Imagine that you have a pitcher of water and you want to fill it all the way up. How much water will it hold? If your pitcher is shaped like a cylinder, it will be pretty easy to figure this out before you ever put a single drop of water into the pitcher. The total amount of space inside an object, like your pitcher, is called its volume. What if you now decided you wanted to paint the outside of the pitcher a different color? How much paint would you need to use to cover the whole outer surface of the pitcher? The area of the surface of an object is called its surface area. For simple geometric shapes, like spheres, cylinders, and prisms, it's pretty easy to calculate both the volume and surface area, as you can see with these formulas and their images. As the object gets bigger, it makes sense that both surface area and volume would get bigger too. However, can you guess which one will get bigger faster? For example, if you double the radius of a sphere, will the volume also double? What about the surface area? Which one will increase the most, or will they increase the same amount? Let's look at a few examples and see if we can come up with some general rules for how changes in dimensions will affect the surface area and volume of an object. How much would the volume of a sphere change if you doubled the radius? Would it also double? Let's calculate the volume of two spheres, one with a radius of 1 meter and the other with a radius of 2 meters, and see how the volumes compare. As you can see, for the first one, we use the formula 4/3 pi r cubed, and after plugging in 1 meter, we get a volume 4.19 meters cubed. And with the second one, we get 33.51 meters cubed. So therefore, the second sphere's volume equals 8 volumes of the first sphere. Wow! When the radius of the sphere was doubled, its volume increased 8 times. Was that more than you expected? The volume increased so much because the radius is raised to the third power. This makes the volume increase much faster than the radius. Even small changes in radius can cause big changes in volume. Does the same thing happen for surface area? Let's calculate the surface area of the two spheres and see what happens. As we can see, after plugging the values into the formula 4 pi r squared, we get 12.57 meters squared for sphere 1 and 50.27 meters squared for sphere 2, making sphere 2 equaling 4 sphere 1s. The surface area did increase when the radius doubled, but not as much as the volume. Can you guess why that happened? In this case, the radius is squared, and when calculating volume, it is raised to the third power. As you can see, this makes a big difference. Both surface area and volume increased when the radius was doubled, but volume increased a lot more. Does the same relationship exist for cylinders? Unlike spheres, cylinders have two dimensions that can change, radius and height. Changing either one of these is likely to also change the surface area and volume. So this time, we need to change just one at a time and see what happens. First, let's start with a cylinder with a radius of 1 meter and a height of 1 meter. How would the surface area and volume change if the height was not changed, but the radius was doubled to 2 meters? As we can see, the first cylinder's surface area is 12.57 meters squared, and the second cylinder's is 37.70 meters squared, while the first cylinder's volume is 3.14 meters cubed, and the second cylinder's volume is 12.57 meters cubed. Just like we saw for the sphere, both surface area and volume increased when the radius doubled, and volume increased more than surface area. However, neither increased as much as they did for the sphere. Now, what about changing the height? Let's go back to a radius of 1 meter and see what happens to the surface area and volume when the height doubles, going from 1 meter to 2 meters. As we can see, the first cylinder's surface area is 12.57 meters squared, and the second cylinder's is 18.85 meters squared. The first cylinder's volume is again 3.14 meters cubed, and the second cylinder's volume is 6.28 meters cubed. So once again, both have increased, and volume increased more than surface area. However, it's pretty clear that radius had a bigger effect on both the surface area and volume of the cylinder than height. Next, let's see how changing the dimensions of a rectangular prism affects the surface area and volume of the prism. Let's start with a prism in which all sides have a length of 1 meter, and then see what happens when we increase the length of each side to 2 meters. As we can see, prism 1's surface area is 6 meters squared, and prism 2's is 24 meters squared, while prism 1's volume is 1 meter cubed, and prism 2's is 8 meters cubed. So, just like for the sphere and the cylinder, when the dimensions change, the volume changes more than the surface area. Finally, we will see how the surface area and volume of a pyramid can be influenced by changing the dimensions. Once again, we will start by calculating the surface area and volume of a pyramid, in which all dimensions, length, width, and height are equal to 1 meter. And then compare those values to those calculated when the dimensions are equal to 2 meters. As we can see, Pyramid 1's surface area is 4.24 meters squared, and Pyramid 2's surface area is 12.94 meters squared, and Pyramid 1's volume is 0.33 meters cubed, and Pyramid 2's volume is 2.67 meters cubed. At this point, you're probably not surprised to see that the trend we saw for the other shapes continues for a pyramid. Both the surface area and volume increased, but volume increased a lot more. Alright, let's take a moment to review what we've learned. As we learned, the total amount of space inside an object is called its volume, while the total area of the surface of an object is called its surface area. Surface area and volume can be easily calculated for simple geometric shapes, like spheres, cylinders, and rectangular prisms. When the dimensions of the shape, such as radius, height, or length, change, both surface area and volume also change. However, the volume of the object always changes more than the surface area for the same change in dimensions.